Hello and welcome to this new video. Today we are going to talk about Linux from nothing. Big brain moves coming up. So yes, today we are talking about Linux from nothing. So our goal will be to make the most minimal system possible using Linux. So we are going to go through all the steps, all the pitfalls, and everything that we need in order to make a system work. Now we are going to use the kernel, we are going to use Bash, Core Util, Util-Linux, Nano, Glibc, and Ncurses. We are going to make an Init, we are even using Grub. So all of those tools we will know how to compile, how they work, and how to install correctly on our system. So to start that process, we first need to install everything that's needed to compile and prepare our LFN. Now this of course is using apt, so it works on Debian or Ubuntu, but if you are an Arch user or whatever other distro that you like, you can test with your package manager and copy me the right command so that we can share it with others. Now let's get started and actually make a directory. So we are going to use the mkdir, which make a directory, and let's name it LFN. Now let's enter that directory using the cd command with cd lfn. Now let's make a root that will be the root of our future file system, and let's enter that root. Now let's just build a skeleton of our actual file system. Let's make a boot directory, a proc directory, a sys directory, and a dev directory. Those are all pretty much system directory. We won't mess around them that much. We will of course put the kernel inside of the boot directory, and if we were to have an init-ramfs, we would put it inside of the boot directory. But for this tutorial, we won't use any init-ramfs or initrd. Now let's make the usr directory, which will contain all our libraries, all our binaries, and pretty much everything that our system needs to run. And let's enter that usr directory. Let's then make our lib directory, lib64, bin, and sbin, which will contain those programs and libraries, and let's back out of them. Now we will need to create symlinks between those usr directories and the root directory. The reason why we need to do this is there's a lot of program that actually assumes that everything will be in the root, and there's a lot of other program that assume that everything will be inside of USR. Now most modern program will assume that everything's in USR, but we still keep the links because it's pretty much assumed that it will always be there. So ln-s allows us to do a symlink, and let's do it for lib, lib64, bin, and sbin. Let's just take a look at what we've done. We have created the dev, proc, sys, and boot, and we have our symlinks that point to the directories inside of the USR, and we have USR that is full of those directories. Now that we've created that skeleton, let's back out of there and let's create a variable. So export allows us to create a shell variable. So let's create the lfn variable and let's give it the path to our root. So it needs to start with a slash. It needs to be starting from the real root of our system going to the root directory that we have inside of our lfn project directory. Now the reason why we are doing that is because it's way faster to write $lfn to call that variable than writing that full directory each time. And we are going to call that variable a couple of times in this tutorial, so you don't really want to have to write it in full each time. And also keep in mind that if you are exiting this shell that you are using, this terminal that you are using, you will need to call this variable again. So don't try to run some kind of command with $lfn if you close the terminal and open it again, because of course you've lost the variable. You need to rewrite it instead. Now let's start by the beginning, which is the kernel. Let's use git clone with the dep1 option. The dep1 option allows us to only download the latest version and not all the modification in between, so it makes things way faster, less bandwidth, all positives. So let's download the latest version of Linux. You could use any version that you want, and that's true for any of the programs today. You can download your own version if you want. You can go ahead and not use the latest. We will use the latest for pretty much everything in this tutorial, but if you want a specific version, go ahead. There's no real limitation in this tutorial. Now let's go inside of the Linux directory that we have downloaded and let's do make tinyconfig. Tinyconfig is there to give us the tiniest config possible that will still be able to be compiled. That will allow us to then modify that tinyconfig and get the most minimal version of Linux that's able to run on our system. So let's do make menu config now to be able to modify that configuration. Now our goal today today will be to be able to run our Linux system onto a 64-bit QEMU VM. So QEMU uses some special virtualized hardware that we will need to enable. This hardware uses a virtualized version of PCI, and it will also need to be compatible with ext4 and be able to write on the drive that we will provide it through QEMU. So to be able to do that, we need to enable a few settings. Now let's start by going down General Setup, configure standard kernel feature, and then enable support for printk. Printk is the way of the kernel to communicate with us. It will be able to yell on the terminal, hey, something is going on, or hey, something bad is going on, something good is going on. Whatever happened, printk will be able to yell at us. If we don't do that, the kernel will be silent, and we may have a lot of questions if there's an issue going on, or if there's a kernel panic, or whatever happened. We won't have much information. Printk makes communication happen, and it's necessary for us. Now let's back to the root, and let's go enable the 64-bit kernel. Of course, if you're on a 32-bit system, you don't enable that, but for most of you, enable 64-bit kernel. Now let's also go down and enable the block layer. The block layer is the way of the Linux kernel to communicate between your hard drive and the rest of the system. It is needed in order to get data. So of course, we will use an ext4 file system on a drive. So to make that communication possible, we need to enable that block layer. Now let's go down to executable file formats, where we will enable both kernel support for ELF binary and kernel support for script starting with a shebang. Now ELF binaries are pretty much all binaries. Most binaries will use the ELF system, so we need that in order for it to work. Now the kernel support for scripts starting with shebang, our init will use a shebang. A shebang is the way for the file to say, hey, I want you to execute me using that command. So you don't have to actually use a specific command in order to execute it, because if you execute the file itself will already tell you how to execute it. Now let's back out and go down to device driver, where we will enable, of course, PCI support for our drive, and we will go on to generic driver option, where we will enable both maintain a dev temp fs file system to mount at /dev and auto mount that /dev. So this will allow us to have a working /dev. Then we can back out of there, go down to serial ATA and parallel ATA driver, libata, and make sure that you enable it. Now this is the standard driver for SATA or IDE. We need that in order for our drive to work. And now let's enter that option, and let's go down to Intel, ESB, ICH, PIIX3 and 4. I believe that our QEMU will use PIIX3, so a virtualized version of that. So we actually need to enable it, or else our drive would not be found. Now that we have enabled that, we have enabled everything so that our drive can be recognized through the PCI system, but we have not said to the system that we will actually allow drives to work. So let's go back up and go into SCSI device support and enable SCSI drive through the SCSI disk support. This will allow us to actually see the drive and not just, hey, I have a drive and I have no clue what to do with it. Now we will actually be able to do something with it. So now we can back out of there and go down to character devices, where we will enable TTY, which allows us to have an actual terminal that we can use, and go down to serial driver, where we will enable the serial driver for 8250 and the console on that 8250. That allows us to A, have a terminal, B, have a terminal that shows something on the screen and is compatible with QEMU. That allows us to actually communicate with our kernel. Now we can back all the way up to the root, where we will go down to file system, we will enable ext4, and we will go down to pseudo file system to enable both proc and sysfs on our system. With that, we have a full system ready to go. We now need to exit that config and actually compile our kernel. To do that, we will use the make command using the make-j8. Now that 8 number you can change, because I'm using it that way because I have 8 cores. If you have 4 cores, you would use the -j4. If you want to compile it on 1 core, you could do, well, just make, or if you want to do it on 2 core, -j2. You understand the gist of it. More core you have, the higher the number you put there. Now, once it's compiled, it will take time, but once it's compiled, you can use the move command to move our kernel from the Arch x86 boot and all the way back out to the project directory. Now let's ourselves back out of there, and let's take our image and actually throw it inside of our root and inside of our boot folder, so that we can actually put it at the right place where we need it for future use. So with that, we have a fully working kernel that's put at the right place inside of our file system. So let's actually move to the next step in our LFN build, which is bash. We need a shell in order to communicate with our system, because right now with only a kernel, well, even if we have access to a terminal that would be able to maybe give our input somewhere, we have no program to be able to take our input and throw it against the kernel or throw it against another bunch of program. We just have a kernel, right? It's not able to speak, it's not able to do anything, so we need something in between that's able to translate what we say and get back some information. So this is where bash chimes in. So let's use the git clone command again with the def1 to download our latest bash, and let's do a make directory bash-build, and let's also enter that bash-build command. Now pretty much all of the software that we will see today will be compiled in fairly the same way. It will use a configure, it may use a bootstrap or an autogen, but that's something that we will see for the next software, but they will all use something like a configure. So the way that we are set up, we have one folder with our source, which is bash, and we have one folder that will be full of our compiled file or our compilation file, which is bash build. So if ever you were to, I don't know, want a new configuration on your bash build, you would be able to delete bash build and recreate a new one and reconfigure it using the configure command. So you don't have to re-download your source in order to redo a configuration. That's why we put everything in a separate directory. Now, the configure command is a complete command that shows us all the little features that are able to be enabled or disabled from a given software. So with those options, we can say, hey, I want that library enabled, I want that library disabled, I want that feature, I want that feature gone. So with those options, we are able to fine-tune our system in order to have truly what we want. Now, of course, you would use the configure --help in order to see all of those configuration, but today we don't really want any special configuration. So let's actually use the configure, and with the option prefix. Prefix only tells configure that we will end up with the root directory of the program to be USR. So we want configure to install our system inside of /USR at the end of the day. That's our goal, right? We want it to be directly at the right place. This is why we tell the system inside of prefix. So once we launch that command, it will generate what we call a makefile. Now the makefile is a little bit what we use with the Linux kernel already. It enables the make command to do anything to start working, right? And that makefile will be generated off the information that we give configure. So all the fine tuning will be automatically put inside of the makefile. And a makefile in reality is just a bunch of instruction on how you should go about compiling the software. So it will group a bunch of commands that are there just to compile something in a pretty standard way, right? We want a standardized way to compile. The configure will create the makefile. The makefile will tell us how to compile the whole system, and then we can just use make-j8, just like we did with the kernel, to actually compile our bash. So just like the kernel was before, we are left with our executable inside of our bash-build directory. But that's not where we want them, right? We want those executables to be placed at the right place inside of the USR directory. Now to do that, we will use the make install command and using a specific option, which is destdir. Now we are using destdir $LFN. Remember, $LFN points to the root of our future file system. So the reason why we're using that is because we don't want to install it on the running system, because right now our running system is our Ubuntu machine, right? We don't want to install it there. We want to install it directly inside of our LFN installation, and this is what destdir is there to do. It's there to tell us, hey, there's a new root, and then it will be able to put the files at the right place, still following what is written inside of the prefix option that we've given configured. So now that we've done that, we can back out of our bash build directory, and right now we should have a bash executable inside of our bin directory. But let's go a little bit further. We need a link from sh to bash, because some program will assume that your shell is in sh and not called bash, because there's other type of shells that exist. So let's use the ln-s command to create a symlink. And I think I didn't explain it before, but the first argument on the ln-s -s is what is inside of the symlink, and the second argument is where that symlink is and what's the name of that symlink. So here, what's inside of the symlink is bash, and we put that bash inside of root bin sh. So when you open sh, it will tell, hey, well, you're not at the right place, you need to go to bash. And because we have not put a slash or anything in front of bash, it will know that it's bash inside of the same directory, which is bin, which is where bash is, so everything works. Now let's actually take a look at inside of bin just to see what happened. And using ls root bin, we can see the content and we see, hey, we have a bash and we have sh that is in blue, indicating that it's a link and not an actual file. Now that we have a terminal, let's actually install what we need in order to do simple operation. How do we use cat, copy, remove? All of those commands need to be installed. Those commands are all contained within the GNU Core Utils. So let's go download that Core Util in order for us to use it inside of our project. Let's use the git clone command, and once again, let's do a directory called core util-build, and now let's enter not core util-build, but core util using cd core util. And what we are going to do is do /bootstrap. Now this is only needed if you download it from Git. If you download a real release version, you don't have to do the bootstrap part. The bootstrap part is there to be able to download all that's necessary in order for you to compile Core Util, because Core Util also needs its own little libraries and own little configuration in order to be compiled. And if you have a release version, they will already bake into those information. So when I told you a little bit earlier that sometimes you have a bootstrap or an autogen before the actual configure command, well, that's what I was talking about. So here, because we are using the latest, the Git version, we need to use the bootstrap, and it can take a little while to actually run. But once it's completely run, it will have generated a configure, and it will allow us to just compile like we did earlier. So let's now back out of the core util directory. Let's go into the core util-build, and let's actually use the configure command inside of the core util directory and give it some option that I will need to explain. So we use without se-linux. Se-linux is there to give additional security to a Linux. It adds some policies that are there to say, hey, you can touch that file. Oh, you cannot touch that file. So those configuration we don't need because we don't use se-linux inside of LFN. So let's actually disable it, because if we were to enable it, we would need to add that library inside of our system. And let's not do that. Let's not make our job any more complicated than it already is. And let's do the same thing for libcap. Libcap is another library that is there to give some graphical feature on the user space. Not really important for us, and we don't want to go into adding more libraries for now. So let's disable it to make Core Util as simple as possible to support. And let's again use the prefix /usr in order to install to the right place. Once that's done, we can do the make-j8, which actually compiles the software, and after that's done, we can do make desdir equal $lfn install, which will install it at the right place like we did earlier, and then back out of that directory. Let's now take a look again at our binary directory inside of our root directory. What do we see? A bunch more software, right? Now we have cat, we have copy, we have remove, we have all of those software that are inside of our system that we are going to be able to use to be able to do, well, standard stuff that we need to do, right? So now let's move to a little bit of a more complex thing that we need. We need Util-Linux. Util-Linux is all the tools like mount that we need in order to properly set up our system. So Util-Linux in our case will mostly only use mount. We don't need anything else, but we will still keep most of Util-Linux enabled because it's all good commands that we may need later. So for now, let's clone it using git clone, and let's make util-build, and let's then enter util-linux again to be able to run the autogen. So this is another one that you need to run a quick code before compiling it. Once that compilation is done, you can back out of your directory, go back inside of util-build, and go use the configure file inside of util-linux with some fancy options. So the fancy option that we're seeing here is disable lib last log 2. Now the reason why we do that is again because we would need to add libraries to our system, and we want to make it as simple as possible. We will use libraries, but we don't want to use all the fancy libraries that, of course, gives us features, but features that we don't really care about for now. So let's disable that, and let's, of course, use prefix/usr to tell our program where things go. Now let's compile Util-Linux using make-j8. Let's again install it using make-dir equal $lfn install, and now we can back out of the util build directory. And now let's take another look at our bin folder where we see, hey, we've got our mount program, which is again the only thing that we need for now, but you see it also adds a whole bunch of tools that are there to help us manage our Linux. But for now, the real important one is mount. Now let's go on to our last program of the day, which is Nano. Yes, Nano. Nano is my tool of choice to edit anything text related. Now, some people like Vim, some people like other things, but me, I'm a Nano guy, so that's where we're going. Again, we go with git clone and we copy the Nano source, and then we can make dir nano-build in order to make our build directory. We will again need to go into Nano in order to run the autogen, and once the autogen is run, we can back out of our directory, back into nano-build, and run the configure that's inside of the Nano directory using the prefix option. Now there's no fancy option that we need with Nano because it's a simple thing ever, and we have pretty much all that's needed in order to run it. We need 2 libraries, and I'm going to show them to you right after this. So no fancy features here, no fancy change that we need to do. We only use the prefix option to set its directory. Now we do make-j8 in order to compile, and make-dir $lfn install to install it at the right place. Again, cd ... to back out of our directory. Let's look into our bin directory another time where we see, oh, we have Nano. So now we will be able to use Nano. Now, one big thing that we have not talked about today is libraries, and we need to talk about them. Now, in Linux, you often have a bunch of function that is not included inside of your program. So programs rely on libraries, which are external source of functions and information that are there in order to simplify things, right? We always know that we are going to have this library and this library, so we don't need to package it inside of the program. We can just trust the library. Now, the first and the most important one is glibc. Now, the GNU C library is really important, not only because it contains the GNU C library, but because it contains LD-Linux. LD-Linux is the loader of dynamic libraries. So any other libraries that you want to load dynamically just mean that it's not inside of your executable. So if you want to load any other library at all, you need LD-Linux. So this is the most important library for those 2 reasons. Of course, the GNU C library is standard across everything. If you code anything, you're going to need that GNU C library, but the loader you will also need to be able to load anything else. So let's start with that. Let's again use the git clone, and let's make our glibc-build directory, and let's enter directly that glibc directory and run that configure command from glibc. And let's use 2 options. Let's use the libdir, and we will put it to lib, and let's use prefix again to usr. Now libdir is there to tell the system, hey, we are going to have libraries inside of the lib folder. Now by default, because glibc will be compiled as 64-bit, it will usually look inside of the lib64 directory. With that command, we are telling it, hey, I don't want you to only look into the lib64, I want you to also look into the lib directory. Now this will become really important later. Just keep yourself a little note that this option is enabled and exists, because it's really important to understand how libs work. Now let's again use make-j8 to compile it. By the way, this one is pretty seizure inducing, so have fun with that. Let's skip it a little bit, and let's do make-dir-lfn install in order to place it at the right place. Let's now back out of that directory, and let's look at our lib64 directory, which now contains a bunch of libraries, part of the GNU libc library, but more importantly the libc and the LD-Linux, which, like I said, are needed for everything to run. So don't worry, I'm going to go a little bit deeper on how libraries work, but let's first download our second and last library of the day, which is Ncurses. Ncurses is a library that's there to help us a little bit draw on the screen. So it gives us a bunch of ways to more simply actually throw things on the screen. Now, Ncurses is not only a library, it also contains some binaries binary that we can use in order to make our program, we will still install them, but our focus today is there to use it as a library. Why? Because it's used by Bash and it's used by Nano, both that we have on our system, both that we want to work. So let's start this by actually downloading directly the Ncurses version. Now the reason why we're doing it that way is because they don't really have a Git available to us, at least I didn't find it. And just a quick tip, okay, just a quick tip, if you're listening this a little bit later and you want to search the latest version and you don't want to copy my command, that's okay, but don't use the latest, okay? When they say latest, it's not latest, it's an old version and it's not going to work. Use one with a number on it, right? It can be 6.5, 6.6 when it will exist, 6.7, whatever it is, but it needs a number. Latest is not latest, they have not updated it, I don't know why. Okay, let's continue, where we will decompress the ncurses tar.gz using the tar-xvzf. Now I'm going to be honest with you, the -x is for extract, v is for verbose, z I have no clue, and f is to actually give it the file. So the one that knows what z is will be able to tell it in the comments, or just use the man page, okay? Just read from the manual. Now we will create an ncurses build directory and go into the ncurses build directory where we can run our configure command that's from the ncurses 6.5. And now we have a bunch of options. We have with shared, which allows us to have those libraries. So remember, like I told you a little bit earlier, Ncurses is both libraries and binaries. By default, it will only do binaries. So we need to tell it, hey, I want those libraries. So with shared will do that. Now with termlib will allow us to have the libtinfo, which is needed, I believe, both by Bash and Nano. So that's important. And we also need to enable wide C. C is for character. Wide character are characters that contain more data than 8-bit. So the standard character is 8-bit, but of course we've got character over that. To be able to treat them, we need the wide character option enabled, and it will actually create libraries that will end in W to tell the system, hey, I'm compatible with the wide character because I've got that W on the end. So that's their convention, that's how they tell it. Now that's going to cause some problem that we will actually need to fix, but for now just know that it is with wide characters enabled. And let's use with version sims. What this does is it actually put a version inside of the elf information, which is some information that are accessed when a program tries to use the library. By default, Ncurses won't give you any information about what the library has or what it does, so it will lead to a bunch of issues because all the program will cry out, hey, I need that version and I don't know what version you're running, so panic, right? So this command will allow us to actually have the version put inside of the libraries so we don't have those issues, and it's very important. And let's also use the -- prefix USR to put it in the right place, and then make -j8 to compile it, and the make desdir lfn install to throw it at the right place. And now let's get out of that directory. Now remember when I was telling you that the fact that there was a W at the end caused some issues? Well, let's actually go fix that. Let's go inside of our root and let's create a new symlink using the ln-s command. And let's make a link to libncurses.w.so.6 and let's link that in the lib folder, link it to libncurses.so.6. And let's do the same thing for the libtinfo so that we both have the standard version inside of our libraries, inside of our library folder. Now again, some program will call the W version, some program will call the standard version, but it turns out that the W version can do both the standard and the W version. Now let's dive a little bit deeper into how libraries actually work. So libraries have two ways to be found by Linux LD, the loader that's contained inside of GNU Libc. The first one is the directories that we gave it while we were compiling and its default directory. That's lib and lib64. Remember, we tell through the libdir option, we told glibc to actually look at the standard lib directory and not only at the lib64. So that way, both of those directory, if we have a file or a symlink of a file, it will be able to pick it up and actually use it with a program that requests a specified library. Now there is a second way that the loader also works. It can also look into the cache in order to know if a library exists exists and then use it for a program that would request it. Let's make an example for that. Let's create a file called ld.so.conf inside of the etc directory using Nano. And inside of that file, we will put two directories, /usr/lib and /usr/lib64. Both of those directories should already be covered by our loader because they were baked in, right? Both of those directories are inside of the executable, inside of the loader, so they should already be covered. But let's say that we would want to add another folder, another directory that would be able to load directory. We would just have to add it to the list. Now there is one caveat to that, and we will go back to actually addressing it. But let's first actually create that cache that we need in order to be able to read from both of those directories. We just do the ld-config-v-r and /, and what this will do is it will tell the system to create a new cache. ld-config is there to create a new cache of libraries. The -v will actually yell at us all the libraries that it will use, and the -r tells us where the root should be. Now we are in the root directory, so // is there to tell us, yes, I want the root to be the root directory that we're using right now. So using that command, it will now scan for all libraries that ld-config is able to find, and it will throw it into cache. Now one thing that you will find is that nowhere to be seen is lib ncurse. It's only lib ncurse w that is to be found. Same thing for libd-info, we only have the w version. Now that's really important, right? Because ld-config does not pick up on symbolic link. This is why actually feeding glibc and telling it, hey, you need to look into the lib directory will be very useful, because most of our libraries will be there, and our libraries, we may need to do some cheap hacks like we just did in order to make a library work with a slightly modified version. And if we didn't do that, we would be able to go ahead and end the tutorial, and when we would actually try to run the system, it would do a whole bunch of errors telling us, hey, libncurse doesn't exist. Hey, libd-info does not exist, because actually ld-config would be unable to actually read what's inside of the lib folder, because ld-config would be unable to read the links, the symlinks inside of the lib folder. Everything that would be an actual library would work, but the symlink would not. So this is why it's really important to feed the -libdir argument onto glibc. It's because, like I said, it's hard-coded inside of the library. And the best way to actually see that is to go and execute ld.so, that's inside of the bin directory, and do --l. Inside of it, we will see what are the default lib directory that it will check. So it will check the cache, it will check lib64, and it will check lib because we specified it. So we have those system search paths that we need to specify if we want to have a loader that actually follows symlinks and is not only reliant on cache. By the way, the cache needs to be reloaded, needs to be recreated every time that you add libraries, especially if those libraries are outside of the usr-lib and usr-lib64, because then the system has truly no way to actually take a look at them. So with that, we are done for everything lib related and everything software related. We have everything in place for both of those aspects of our Linux from nothing system. Now we have two last things that we need to do. And that first thing is create an init. An init is the first thing to actually run onto your system. So when you boot up the system, normally something like systemd will init the system and will start managing things left and right, telling what to execute and when. Now in our case, we don't have systemd and we don't have any other type of init. So let's create our own using a script. So let's do nano sbin/init, which is the standard place for an init inside of a standard Linux. And let's actually start filling that file. Let's use the shebang/bin/bash to tell the system, hey, I want you to execute that script using bash. Let's then mount both our proc directory and our sysfs directory so that they can work. And let's then exec/bin/bash to tell the system, hey, I want you to release me a bash terminal that I can actually use, right? I don't want to only be a spectator on this. Let me actually throw commands in, and this is how we do it. Now, once that's done, we can quit that file and actually save it, and then we need to tell the system that init is an executable. So let's do chmod +x sbin/init. So that will tell the system, hey, init is now an executable. That's something that we can now execute. And now let's just leave the root directory. So now we have an init working. Let's actually start making our disk and mount things a little bit so that we can actually work on a working disk, so that we can make our Grub, because Grub is a little bit picky on how it works. So let's start by using dd in order to make a disk. We do dd input file equals dev/0, output file equals disk.image, block size 1 megabyte, and the count is 1024. You can give it the count that you want, but in our case I want 1 gig of file, just so we have some room that we can use in order to expand later. Now let's use a command called fdisk. Fdisk is there to format a disk. So let's do fdisk disk.image, and then it will ask us, hey, what do you want to do? We do n to create a new partition. It will ask us what type of partition do we want? We want a primary, so let's do p, and then it will ask us what's the number of the partition. We want it to be number 1, so first partition, and then it will ask us both when do we want our partition to start, leave it default, which should be 2048 sectors, and then where should it end, leave it default, which is the full disk. Now after that we will do a, where it will mark the partition as bootable. So a tells the system, hey, that first partition is actually a bootable partition. And then we do w in order to write those change to our file. Now that's done, we can actually start mounting things. So let's start that process by using sudo, because now we need super user privileges, lo setup -f P --show disk.image. What this command does is it will set up a loopback device. Loopback device are a way that we can actually mount a file to a point on our system so that we can interface it a little bit like we would for a standard disk that we would connect to our system. So the -f will make sure to find the next available loopback device that we can use, because on some system you could have a lot of loopback device in use, especially if you have snap, you know what I mean. And the P will allow it to search inside of your image to find different partition and map them to P1 or P2 after the loopback device. I promise it will make sense where we will use it in the next step. And --show just tells the system, after you're done, just please yell the loopback device that you're actually using so that we know where you're going at. So let's actually use that command, and we see, hey, we've got a loopback device, loop 10, that we can use. So let's use it to start formatting our disk, because what we've done in the prior step is actually just tell the system, hey, there's a partition there, but we don't actually have a formatted partition. It's a blank partition. It's not ext4. It's not nothing else. It is a blank partition. So let's actually format that partition. For that, we use sudo mkfs, so make a file system.ext4/dev/loop. Now your loop number, in our case, it's 10 p1. P1 because it's our first partition. So what I was talking about, it generates automatically depending on how many partition you have. So it makes things simple for us. So /dev loop, your loop number p1 in order to format using ext4. Now that we've made that, we can actually mount that partition to a physical place on our drive. So let's do sudo mount /dev/loop 10 p1 and mount it to /mount. With that, we will be able to copy our data from root to the /mount directory. To do that, we use the sudo cp-R root/*. What it tells is the content inside of root, and we transfer that to /mount/. That's important because it tells us we want to take the content of root and throw it inside of mount. And sudo is important because normally when you mount a fresh file system, it will normally require root privileges. So now what we have is a mounted file system with all of the data needed for it to run, but we have no actual way to run for our partition to know to execute itself, right? We need a bootloader, and that bootloader is Grub. The job of Grub is to take your system, your computer, when it boots, it will read the early part of the drive called the bootloader, and it will attempt to know where it should go next. And Grub is there to direct it towards the right place. So we will use this long and complex command. Let's just go through it and understand it, right? So sudo, we need super user privileges. Grub install, that's the name of the command. Target, we use i386pc. The reason why I'm using this is because I don't want to use EFI, and by default, most system will actually use EFI if you don't specify the target. So I do i386, which is the standard non-EFI way to run it. And let's do --root directory, which our root directory is /mount. We tell it no floppy because we don't want it to search for possible floppy, right? The floppy command is there to, at boot, be able to find, oh, do I have other places that I can go? We don't care about other places. There's no other place. There's only our drive. So no floppy kind of restrict what Grub can do. And then we will add modules onto it. So our modules that we will use are normal, which pretty much says what it is. It's normal to use it. And we have part MS-DOS. Our partition system that we're using is not .gpt, not chat GPT, but the partition system. There's a partition system that's actually called GPT, and we're not using that one, we're using MS-DOS. This is the part that we were doing using fdisk. So fdisk by default actually use MS-DOS formatting, so we need to be compatible with it. That's why we use part MS-DOS. Then we need ext2. ext2 is just the name of the driver that accepts ext2, ext3, ext4. So if you have any of those file systems, you need to include it inside of Grub. And then we use multiboot, which is needed in order to use all of the menu entry function that we will be using. Then we do /dev/loop and our loop number. Take note, we're not putting a partition here, just /dev/loop 10 in our case, but in your case it may vary. Like I said, no P there because we want to install at the root of the possible root in the bootloader of our drive. So now that we've created that, it did two things. It actually put some code into the bootloader of our disk.image, and it also put some code inside of our /mount/boot. So now let's actually put some configuration inside of Grub. To do that, we do sudo nano /mount/boot/grub config, which is the config file that Grub read at boot. And inside of that config file, we will put menu entry, which tells us that it's one of possibly many menu entry. Let's put a name, lfn, and let's put our brackets. Let's now say set root in quote parenthesis hd0, 1. Now hd0 tells us that it's the first hard drive that's on the system, and 1 tells us that it's the first partition on that hard drive. Yes, why didn't they use 0 for both if they start from the 0 instead of 1? I don't know. Okay, they were crazy when they made Grub. Okay, they were a little bit insane. So let's ignore the blatant violation of standard and let's go to our Linux command where we will input where our Linux image is. So linux/boot/bz image. Just remember that by default bz image the I is capitalized, and then we have root equals /dev/sda1. The reason why we need that is we need to remind the kernel that it's supposed to actually mount a file system here, and that file system should be on the first disk that it actually finds. And after that we have rw, which tells the Linux kernel that this hard drive should be in read and write permission. It should not be read only, you should be able to write on it. So now we can do Control X and Y to be able to save all of that. And right now you kind of have a choice if you have other tutorial to follow, because you're in the future and you actually follow other tutorial. You can just spam sync a couple of times. The sync command is there to tell your system to write the cache on disk and not actually keep it inside of the system. That's important because if we were to emulate it right now, our disk.image, there's chances that there's going to be file missing because they're not written. So spamming sync a little bit will force the system to actually sync it on the drive. Now, if you want to be 100% safe, you can do sudo umount/mnt to unmount the partition and do sudo lo setup -d/dev/loop with the loop number, which will destroy our loopback device. So then everything is confined into the disk, and of course there's no cache here because everything has been written as we unmount and destroy loopback device. So now we can actually run our LFN. Woo! Let's actually have some fun here. So let's use the qemu-system-x86_64 to run disk.image. And here what we should see is a working terminal that can do clear, that can do ls of various directory, and we can even create a file. So let's create a file using Nano, for example, and write it and save it. And the sync command is there too, so we can sync it to make sure that it's okay. We can quit. Now I used Control D, which of course crashed the system because there's nothing else than bash on it. You can close it and actually open it back up, and you should see the same data on it, right? We have the lol file that's still there with the same data on it. So everything's working. You have the smallest, simplest possible Linux. So that's our base. That's where we're starting from. Our next tutorial will focus on actually building upon that. So for now, we have the smallest, simplest Linux possible. And that's all something that you now know how to do. So I hope that you enjoyed this video. I hope that you learn throughout that process. And I gotta say thank you to everybody listening and to everybody making a bunch of comments. I know that the preparation towards this video had a lot of hype and that a lot of people were interested into going deeper into every aspect of Linux from nothing. So I hope that for now I'm giving you what you want. And of course, always tell me what you want to see next in the comment. And let's do a little word at the end, okay? If you've watched until then, just write sync, or better than that, write sync 3 times. That's going to be funny, right? Sync, sync, sync. Okay, that's where we're going. That's our our code. That's how we know that you are a big brain, okay? You've went through it. You now understand everything there is to know to how to make a small Linux system. So I'm going to probably make a video on another subject before going on to making the next version of the next upgrade to LFN, or maybe not, I don't know. But anyway, just tell me what you think, what you want to see next, and I hope you enjoyed, and of course, take care.